to join. So good afternoon all. This is my third session for the AICTE GATE classes. We are teaching environmental engineering. So environmental engineering first part, that is water supply and treatment engineering, almost completed. And second is the part is the wastewater engineering actually. So in the previous two lectures, we have covered the water supply and treatment engineering part, including water treatment, plant unit operations, and water characteristics. Some remaining portion, like primary treatment and primary treatment and secondary treatment plant treatment operations, something is remaining. So that we have covered till sedimentation, primary sedimentation tank. Now we are moving for the filtration and disinfection. After that, we'll cover the water distribution network, how to design a water distribution network for the treated water for the community. Then we'll move for the wastewater engineering part. So this is the third session. These portions we have discussed last time, all the water supply, water characteristics, physical, chemical, biological characteristics, and unit operation of water treatment. We have done some numerical portion also. Aerations, sedimentation, plain sedimentation, followed with coagulation, without coagulation, settling of discrete particles. These Stokes law of discrete particles we have discussed. So these things we have covered. Sedimentation tank theory. The last portion we have done how to design a sedimentation tank. And these are the flow rate and various hydraulic parameters that we have designed, and these are the various formulas we have discussed last time. Okay, sedimentation tank design. These portions we have covered last time. So cross-section design of sedimentation tank, followed with sedimentation tank. Typical dimensions of sedimentation tank and these various parameters like surface flow rate, time of horizontal flow, detention time of, or we can say the HRT, hydraulic detention time. So various numericals also we have done last time. Then hydraulic efficiency also, particle removal efficiency also we have discussed. The settling velocity, this is the Stokes law for settling velocity, and then one numerical we have discussed last time. Then sedimentation followed with coagulation. Also, what type of coagulant we are going to add it? What is the function of coagulation? And what is the meaning of physical sedimentation and chemical precipitation? How the impurities will settle down on the bottom, and how the fog will generate? What are the mechanisms in a clarifier? How does it work? And what kind of impurities, mostly the suspended solids, will be removed from the physical sedimentation process? And what kind of chemical process will be taking place, like a Zeta potential, colloidal stability is measured in Zeta potential, and how the colloidal particles, these colloidal particles are negatively charged, and how the chemical reaction will take place. These mechanisms we have discussed last time. Is that PPT visible? Can you see the PPT? Akash, PPT?
Yes, sir. Yes, sir.
How the negatively charged impurities will react with the coagulant added, and how the chemical reaction will be taking place, and how the impurities will settle down due to the physical sedimentation, right? So these all those things we have studied last time. And what type of impurities will be removed from the coagulant operations? Common coagulant that you are going to use it: ferrous sulfate, alum, ferric sulfate, and ferric chloride. These all those things we have discussed. So I'm just quickly revising the what we have done last time, so it will be easy to understand for the further process. These things also, that what test is required for the coagulation. The jar test is very common. What are the mixing? How you will mix the coagulant in a flash mixing chamber, and the rapid mixing and slow mixing, right? So then these are design of clariflocculator. So last time we have designed a clariflocculator. So various parts we have designed it. What should be the flow velocity? What should be the settling velocity? What should be the surface overflow rate? What should be the detention time? These are the all those things we have done last time. This is the design of clariflocculator, design of flocculator. These are the design parameters that you have to take it as the standard design parameter. So detention time you have to take 20 minutes to 40 minutes, and all those things, right? And the settling types, type first of settling, discrete settling, second hindering settling, John settling, that also we have explained last time. So the complete process related to the primary sedimentation tank, even the secondary sedimentation tank also process will be quite similar. Clarifier called as primary clarifier and as well as a secondary clarifier, that also will be common. So then compression settling also, right? How the process will be taking place in 4 types of processes: discrete particles, how it will settle down, and how the fog will generate from the top. These whole processes we have studied last time. Then types of sedimentation tank: fill and draw type, continuous flow type, horizontal flow sedimentation tank. These also we have discussed last time. How you will get the detention time values, the volume of the tank, how you will get it, right? So Q, the flow rate, you will get it, the surface flow rate, the volume divided by discharge flow rate. You will get it. These all those things. This is T actually. T is equal to LBH divided by Q. The mistake we have written it. So detention time for planned sedimentation will vary from 4 to 8 hours, 2 to 4 hours for when coagulant is added. If you are adding coagulant, the process will be faster. So the less detention time will be required for the settling down all the discrete and finally we have done some numerical portion also of design sedimentation tank. These things will remain common for the wastewater engineering also, design of sedimentation tank for the PST and SST. So all the concept will remain similar. Okay. So once you understand this portion, then the PST and SST you can design it easily. Okay. So what is overflow rate? The quantity of water passing per hour per unit plane area is known as the flow rate. This term is also referred as a surface loading rate. So unit will be meter cube per day per meter square. Okay, these things we have discussed. The normally adapted value will be 12 to 18 meter cube per meter square per day. Yeah, you can say then liter, you can write it 500 to 750 liter per hours per meter square for the plain sedimentation tank. And if the coagulation is added with this, then 24 to 30 meter cube per meter square per day. So these things we have discussed last time. So I will be moving for the last. Once the water is treated up to the clariflocculator, we have to send water to the filtration unit where the filtration has to be done. After the disinfection has to be completed. Okay, so these all those things you may have shared this PPT. You just make your own notes, so it will be easy to write the concept from the gate point of view. And these things we have done some numericals last time. Maximum velocity to prevent a scour also we have done it. So like this we have completed the whole part related to the sedimentation design. Now moving for the filtration, this is the next unit operation. So if you have seen, we have started from the aeration. We have the cascade, mechanical aerators, diffusers. You have studies diffuse type of aerators where atmospheric oxygen is dissolved, diffused in the water, so that the bad smell and odor in H2S can be removed. It helps in iron and manganese removal also, some percentage. Then we move for the pre-chlorination chamber where the chlorine is added initially with some initial doses. And then we move for the flash mixing chamber where the coagulant is added. After that, we move for the sedimentation tank. Yeah, we can say the primary clarificator. And then after that, the next process will be called as the filtration. Okay, so we'll move now onwards from the filtration. Just I'll check. Please join the class. How many are there? 10 are there. Okay. Yeah, so that was done previously. Now we'll move for the filtration. After filtration, I will move for the disinfection. Quickly, we will finish it. Then we will move for the wastewater engineering. Wastewater engineering is nothing. The whatever you are studying right now in this semester. The same thing, but from the competitive point of view, we will quickly revise the formulas and do some problems so you can understand the concept and you can how to approach the concept that is important from the gate point of view. Okay. So what is filtration? So water flows through a filter designed to remove the particles from within it. The filters are made of layer of sand and gravel, and in some cases crushed anthracite. Filtration collects the suspended impurities in water, enhancing the effectiveness of the disinfection. So if filtration chamber you are going to provide, what are the main function for filtration? The more fine suspended solid in colloidal solids which cannot be removed from the sedimentation process, we can remove it through the filtration process. So that's why for removing a fine suspended solids in colloidal substances, we have to propose a filtration unit. Okay, in filtration, some kind of bacteria also and pathogens also will remove in a filtration process, some percentage. Okay. The second step in the conventional water treatment system is filtration, which removes particulate matter from the water by forcing the water to pass through the porous media. The filtration system consists of filters with varying size of pores and is often made of sand, gravel, and charcoal. We will be having a filter media based on the sand, gravel, and charcoal. So gravel is having a different size, particle size distribution will be different for the gravel. Sand will be having more. So then the lower you have to put the larger particle layer. The higher the layer, you have to filter the water coming out from the primary sedimentation tank. So we'll go in detail. The diagram below shows a homemade filter that is made of the particles of less than 0.1 millimeter would pass through the fine sand layer. This filter will not be able to produce safe drinking water because many contaminants are much smaller than 0.1 mm. So even in filtration techniques, some viruses and bacteria and pathogens are also captured, and that's why filtration is effective. There are two basic types of sand filtration. We called as slow sand filtration as well as the rapid sand filtration, right? So we'll talk about the slow sand filtration design, parameters, as well as rapid sand filtration. First, we have to understand the objective why filtration is required. Then you have to understand how to design a filters. So there are the two types of filters: slow sand filter as well as rapid sand filters. And then how to make the beds, how to prepare the bed of gravel, bed of sand, and bed of anthracite, whatever. If you are taking a charcoal, depend. So these impurities consist of suspended particles, fine silts and clay, biological matters, bacteria, plankton, spores, crust, and other material, and flocks also, of course. The material used in filters for the public water supply is normally bed of sand, coal, and other granular substances, as I told you, maybe charcoal. So we'll talk about the on basis of two types. There are the two basic types of sand filtration based on the force by which filtration is carried on, which called as the gravity filters. Number second is the pressure filters. Okay, and based on the rate of filtration, we called as means the volume of water filter per unit time per unit surface area. We divide in two parts. One is the slow sand filtration, another one is the rapid sand filtration. And third one is based on the number of media employed: single media filters, dual media filters, and multimedia filters. The media that you are going to provide it for the sand, gravel, as well as the charcoal in anything, right? So what is slow sand filtration? Slow sand filtration, the efficiency for removing the pathogens, bacteria, yeah, we can say the biological efficiency is higher than rapid sand filtration, right? So in this slow sand filtration, what will happen? It's a biological process because it uses bacteria to treat the water, and the bacteria establish a community on the top layer of the sand and clean the water as it passes through. And by digesting the contaminant in the water, the layer of microbes is called as biofilm. It's a Dutch name, called as how you will pronounce. So it's a biofilm which will be on top of the layer on the sand, because sand will be having a smaller particle than gravel. So the first layer will be working as a biofilm. It will capture all the microbial bacteria in their pores, and it will help to remove these bacteria. So it helps in biological treatment of municipal water, and requires cleaning every couple of the month. When it gets too thick, the flow rates decline. After this biofilm is removed, the bacteria must be allowed several days to re-establish the community before filtering can resume. So large areas is required for this slow sand filtration. Biological removal efficiency is higher than the rapid sand filtration. There will be the biofilm on the top. You have to replace, or you have to clean this biofilm periodically, or sometimes you have to remove this layer completely and then you have to provide the fresh layer, because maximum number of bacteria will be captured in this first layer of biofilm. Okay. The flow rate of water is between 0.1 to 0.33 meter per hour due to the land area that is required and the downtime for cleaning. I will talk about the cleaning of how we are going to clean the rapid sand filters and slow sand filters later on. First, we have to understand what is rapid sand filtration, what is slow sand filtration. And what is rapid sand filtration? It's a physical process that removes suspended solids, fine suspended solids from the water. Rapid sand filtration is much more common than the slow sand filtration because rapid sand filters have fairly high flow rates and require relatively little space to operate. In fact, during rapid sand filtration, the rate up to 20 meters per hour. And are put back into the operational immediately. We'll talk about the backwashing and squaring mechanism of filters later on. First, you have to understand, if you compare the rapid sand filtration and slow sand filtration, rapid sand filtration need to clean twice in a day, or in a week at least 4 to 5 times. But in slow sand filtration, that much is not required. And the particles that are removed from the water during filtration depend upon the size of the filters that are used. Slow sand filters remove bacteria, protozoas, and viruses, as I told you, and produces essentially clean water. Through it is still advisable to use a disinfectant as a precautionary measures. After that, for removing these bacteria microbes, we are going to propose a disinfection process, chlorination and ozonation. That is another process, but still, if you reduce this biological food versus food by microorganism ratios, FIM ratios here, then it will be easy to disinfect in the further process. Then rapid filters remove suspended particles, as I told you, which may have bacteria attached, but in general does not remove the bacteria, protozoas, and viruses, because as I told you, it's a physical filter. In water treatment plants, filtration removes a large number of contaminants, but it still requires disinfectant to produce the drinking water that is safe. That is the next process. So the rapid sand filtration cannot effectively remove the bacteria and viruses. It is an important step in wastewater in water treatment process. Like coagulation, filtration can remove the suspended and dissolved matters present in the water. And the disinfection process is more successful for reducing the amount of chlorine, that we'll talk later in the next process. The commonly used media, as I told you, sand, gravel, silica, anthracite, coal, charcoal, garnet, or green salt. India silica sand is very common for the rapid sand filtration and slow sand filtration as a filter media. Treatment process and basic design principles, if you see, for the rapid sand filter as well as the slow sand filters, what process will be happening inside. a combination of flocculation and coagulation, sedimentation, filtration and disinfection. Like this, you will be moving. If you see the complete water treatment plant, there will be aeration, then pre-chlorination, then flash mixing, the rapid mixing chamber. We can say the coagulant doses are added in a flash mixing chamber, and then coagulation and flocculation process will be taking place in a sedimentation tank. Then after that, filtration and disinfection process will be taking place. Okay, this disinfection process we'll talk later about the chlorination and ozonation. That's the last unit operation in water treatment plant. As I told you, rapid sand filtration is a physical and purely physical treatment process, and slow sand filtration is completely a biological treatment process. As the water flows through the several layers of the coarse grains, sand and gravels, relatively large particles are held back safely. The major part of the gravity rapid sand filters are: number first is chamber, called as a filter tank or filter box that you have to design it. Then filter media, that is sand and gravel and charcoal, whatever the combination you are going to take it. Gravel support, bottom under drainage system, and then wash water troughs where the backwashing is required for cleaning these filter beds. So this is the simple design. If you see that, this is the gravel media, sand, and then gravel and anthracite or maybe charcoal. You will make the various medias. Water will be coming, raw water inlet, and then backwashing will do later. And then filtered water will be coming out after filtering operations, and it will be sent for the disinfection purpose. Backwashing is required for cleaning these filter. From the bottom, there will be the sprayer mechanism with the high pressure jets. Water will be sprayed in these bed filters. So in the pores, whatever the impurities are deposited, whatever the suspended solids will be deposited or bacterial components will be deposited, will be removed, and then finally this dirty water will be sending out for the primary operations. So it's in a closed loop actually. This through the backwater coming out, backwash water coming out after cleaning this filter will become dirty. Again, it will send for the primary treatment. So this is the design of complete disinfection filtration. This is the various water drainage chambers. These are the chambers. Two chambers given here. Operating flow tables, rate of flow and loss of head, filter bed, wash, water trough, concrete filter. This is a civil structure actually. And then below pipe network has to be incorporated. From there, the backwashing has to be completed. This is the cross section for it. Gravel bed cross section. This is the bottom trough. Then graded gravels, filtered sand, and wash trough. These are the various layers. Perforated layers will be provided here. Cast iron manifold and floor, filtered floor. And the drainage system will be down uh, below the tanks, and then the dirty water will be recirculated. These are the actual filters in the conventional water treatment plant units. So there's various chambers, 1, 2, 3, 4, 5 like this, and 1, 2, 3 like this, and in a line in a parallel combination we used to. It's a combined process. All the water is recirculated in the common water connection. Water drainage system has to be provided. Will be a detention period also. Some detention period will be provided for the water coming out from the sedimentation tank. These are the physical pictures. This is the rapid sand filter. You see the more clear picture with duct under drainage system. Bottom we will be having a drainage system. You can also do as a project here in our engineering also. In the small sections, cross sections of filter, rapid sand filters, you can make it. Even you can design it. It's not a complicated that much of scientific knowledge. We don't want here any IC engines and electronic circuits and nothing. It's only the physical design and water drainage system you have to provide it, in various chambers you have to provide it, including with the various gravel structure. So you can also take it as a project here. So rapid sand filtration components with gravel and perforated pipe under drainage system. These are the cross section designs that we have made it. These are the gravel structure. Here's a trough we have provided, wash trough, filter tank. If you cut section, if you go for it, this is the filtered water to clear well. It will go there, and you see there. This is the structure of coal, anthracite on top, then sand, then garnet, then coarse gravel. Like this, you can get water will be coming out from the primary sedimentation tank, and then it will be filtered out in the layer. And through the drainage system, filtered water will go for the disinfection chamber. In the design part also, you can see that. See, the person is making this gravel bed, perforated, and all the arrangement he's making for the under drainage system, including with the nozzle for the backwashing. He's arranging it. So for backwashing, water has to be sprayed from the bottom on the bed, because the main function for backwashing to clean the filter beds, actually, to remove the to open the pores and these voids available in that. So these all the impurities will wash away with the drainage system, and the filter bed is ready for the further treatment for the fresh discharge. And what are the mechanism of filtration? Number first is the mechanical straining. Number second is the sedimentation process, then impaction, then interception, and then fifth one is the biological metabolism. The filter chamber is usually made out of reinforced concrete filled with the sand and gravel to a height of 1.5 to 2 meter. Various combinations are available. Rectangle tanks generally we will make it. The water is supplied to the top of the sand bed and filters as it flows through the layer of the graded sand and gravel. A system of perforated pipes on the bottom drain the chamber. The filter chamber can be constructed as open tank in a rapid sand filters, a rapid gravity filters, or maybe a closed tank as a pressure filters. This filtering process is determined by two basic physical principles. The first, relatively larger suspended particles get stuck between the sand grains as they pass the filter media, which is called as mechanical straining. The second, smaller particles get stuck to the and we can say the physical absorption processes, because learning is also it will be filled down in the pores and it will be captured layer by layer. And the physical van der Waals forces, that's a physical absorption method, it's surface absorption method actually. And then water will be treated in various stages. If I'm going for the design of rapid sand filter, so for the single media gravity types of filters, rate of filtration will be 3000 to 6000 liter per hour per meter square. Just a second. Okay. These are the standard parameters that you have to take it while you are going to design it. The rate of filtration, you have to take it 3000 to 6000 for the single media gravity filter. For if I'm going for the rapid solo sand filtration, you have to take 30 times more than this. Okay, because remover the efficiency will increase here. So particle removal efficiency will be 80 to 90% in a rapid sand filtration. If I'm comparing with the slow sand filtration, it will be 98 to 99% slow sand filtration. So biological efficiency, biological impurities removal efficiency is more in slow sand filtration, and slow sand filters are more efficient than rapid sand filters. But the operational and because installation cost for these slow sand filtrations are very costly, and even the maintenance is also very costly in a slow sand filtration. For the these things, pre-treatment and post-treatment of water is compulsory. Directly you cannot send a water for the rapid sand filtration. Water has to come out through the various stages: aeration, pre-chlorination, and then sedimentation. Then it should come for the rapid sand filtration. Not a directly like from the intake structure, we cannot directly treat the water in a rapid send filtration. So component of RSF are, as I told you, filter box, open watertight rectangular tank, size of filter, maybe 10 to 80 meter cube, volume. And bed slope, you have to provide 1 by 100. Depth of the filter 2.5 to 3 meter. Filter media sand, you are going to take it, a silica sand. Thickness of the sand bed, you have to, these are the standard design parameters. Sand bed 60 to 90 centimeter. Effective size of sand, you have to take it as D10, 0.35 to 0.55 millimeter. Uniform coefficient, you have to take is D60 by D10 is equal to 1.2 to 1.8 ratio. So that's all about the RSF. Here the pore space increases, hence the ratio, hence the rate of filtration increases, but the contact with the soil decreases due to less contact with sand. Removal efficiency decreases, as I told you, 80 to 90%. Cu, that for the uniformly graded particles, the coefficient of uniformity will be equal to 1. Every sand grain is effectively involved in particle capture, 80 to 90% of the removal efficiency, and the pore spaces are open. These are the all constraints for this rapid filtration. There's a gravel bed also. Gravel bed will support the sand bed, does not allow the sand grains to escape along with the water. Thickness of the gravel bed standards, you have to provide 60 centimeter to 90 centimeter. Well graded gravel is packed 3 mm to 4 mm. Then there's the under drainage system in the bottom, as I told you. Under drainage system in the bottom that you have to provide it. The closed drains are used to collect water, spacing between lateral 15 centimeter to 30 centimeter cross section. These are the standard design parameters while you're designing a RSF. You see the process, how the process are happening in rapid filtration. We are not in a hurry. Within 2 hours, we'll finish it. Just you can go. We have a lot of things to cover, but we'll see how much we can cover it. Okay. It should not be boring for you. That's why we will go slowly. It should be digested, and you should get a concept study. Okay. So this is the rapid filtration. Make your own filtration here if you want to make the. There's a lot of scope for the filtration and filtration here. It is very easy design. You follow all the standard parameters, and then beds, gravel you can get it, sand you can get it, anthracite coal also you can arrange it, and water drainage system on the bottom you can provide it. Okay, so how the things are happening here. This is the backwash water outlet. It will go for the recirculation activities, as I told you. Trough will be provided on the top to control the flow. So water will be coming in the trough that I have shown you here, no, the troughs. These are the troughs. So water will be coming through the inlet chamber, through the sedimentation tank, your clariflocculator. It will come in the troughs, and it will be coming on the gravel bed. These are the troughs. You see this process, how it is happening. This is the fresh water. It will be coming out through the trough. It will be passing through the gravel sand bed and gravel bed, inlet chamber. And then finally it will go to the gravel bed media. And then it will to the and then finally water will go for the disinfection purpose, and then for cleaning purpose there's a backwashing storage tank, and water will be sprayed through the nozzles. From the bottom side it will spray under drainage system, and then cleaning operation can be done. So open valve 1 and open valve 2, this allows water to flow through the filters. During filter operations, all other valves are closed. Okay, once the capacity is fulfilled, all valves will be closed. There's a detention period you are giving, then again it will be opened. Okay. As I told you in the bottom, you are going to provide a perforated laterals. The total area of perforated should be 0.2% of area of the each filter. The total area of lateral you have to provide 2 times total area of the perforations. These are the standard estimation that you have to take it. standard design parameters. Total area of central drainage is you have to provide 2 times multiply with the area of the laterals. Length of the laterals divided by diameter of the laterals should not be greater than 60. If it is like this, your design is okay. If it is not like this, these design parameters are given in water supply manuals, water supply and treatment manuals, CPHU manuals. So Ministry of Urban Development provides these manuals, water supply and treatment manuals. Even they are having manuals for the sewage treatment plant and wastewater engineering. So in the design, all the design parameter will be given there. Okay. So while you're checking your design is okay or not, you have to go for the various design parameters. That's why it is required. Inlet and outlet chambers. Inlet applies water uniformly over sand bed without distributing sand grains. Outlet central drainage acts as outlet. Other component like a vast water trough, as I told you, air compressors, air pump is required. While we are going for the backwashing process, I will show you. First, the compressed air has to be diffused on the filter bed. Then after that, water washing is required. Okay, there's two operations. First air washing, then water washing. Then the filter will be clean. Then filter will be ready for the next operation. Various valves, rate control devices like ventrimeter you have to provide to measure the flow rate. Head loss measuring devices you have to provide it. Based on these conditions, filter is stopped and washed in every 24 hours to 48 hours. Now, how you will check that filter is required a cleaning? So these are the conditions. You have to stop the filtration mechanism once you found these conditions in 24 and 48 hours. Suppose if you are having a head loss measuring device, if you are getting initial head loss 10 to 15 centimeter, terminal head loss up to 3 meter, and turbidity breakthrough, you are getting 2.5 NTU through the turbidity meter. If you're getting a turbidity up to that level, then you should understand that cleaning is required for the filter bed. When filtration is continued for the longer period, pore space gets closed and head losses increases. As pore space area is reduced, velocity of water filtering through sand bed shoots up and it shears, come up some particles, retains on the filter bed, carries it along with the filter bed. This is the turbidity of filter turbidity breakthrough. So what is the definition of turbidity breakthrough? Continuously using, operation is happening, all the suspended solids, fine suspended solids will be locked in those pores, and pores will be clogged. Water will not go out from the sand to gravel and all that. So it's kind of blockage of filters, right? And this condition, because of this condition, the turbidity will increase in the water. Of course, sand and all suspended impurities will remain in the suspension in the water. Of course, turbidity will increase. And this condition is known as a turbidity breakthrough. Once the filters bed will become saturated for the treating, then this condition will come, turbidity breakthrough. Now we'll come for the backwashing of filters. See the diagram for backwashing. Here is the filtration process in that part. After that, backwashing process is carried out. So fresh water is coming from the top to the trough. It will be discharging on the gravel bed, various media filter bed, and after retention period, water will be filtered and it will be sending for the next operation, that is disinfection and all that. And this is the reverse process, backwashing. Yeah, sometimes we call it a squaring mechanism. Yeah, squaring velocity. So there's a storage tank for the fresh water. Water will be sprayed from the bottom. First, as I told you, air washing is required. So compressor is required. Compressed air is diffused in these filters from the bottom. Because it's pressurized air, it will try to open all the pores in uh, we can say the filter media pores. So it will open, it will try to open, and whatever the impurities are there, it will try to come out on the top layer. Sometimes this top layer has to clean, and then we have translucent filtration. I will talk about it. you have to remove this layer itself, bacterial layer, because if food divided by microbial ratio will be higher, then you have to remove this top layer, sand layer, then you have to replace the layer. Of course, a lot of mechanical devices, pumps, compressors, valves are required for completing this process. And whatever the wastewater is coming out, it can be recirculated for the primary treatment. Then water will again come. There is no wastage here. Okay, so underground drainage system has to provide. And the question is how much amount of water, filtered water required for the backwashing? That should be 2 to 6% of filtered water. Okay. First, you have to do for the air washing, as I told you, it is the first step in backwashing, where the compressed air is pumped through the filtered bed for 4 to 5 minutes at least, which agitates the particles for opening valves F. There's a various representation has been given A, B, C, D, F like this. Here I have shown where it is. Yeah. Now every valve is closed except E and C. Maybe as the E and C I have shown some here. Yeah, you understand the mechanism, that is enough. This increases the pore space, and sand bed gets expanded up to the height ZE. Water collects. This is the height ZE that we have provided up to that here till that point, ZE height, the potential head. And through the relays, other than wall C open, and the total area of represent filtration. Total area of represent filtration required. First, you have to understand the flow rate divided by the rate of filtration that we have given the standard range for it. You have to take it from the parameters. Fix the size of each filter, length and width you have to fix it, and find the number of filters, or fix the number of filtered N required for the represent filtration. So this is the mechanism how you will design a represent filters. Find size of each filter, percentage of filtered water used in backwashing. These all those things we'll do in numericals step by step. Okay. So first you have to find out how much area is required for the RSF. Then you have to find out the Q by ROF ratio. Then you have to fix the size of each filter, length and width. You have to identify, you have to determine, and then find out number of filter beds are required, and filter beds. Then find filter area available, percentage of water used in W, 2 to 6% water used, and volume of water used in backwashing divided by volume of water filtered between backwash. So this ratio also play a very important role while the efficiency of filtration is considered. So how much volume of water used in backwashing? That is suppose 2 to 6% of total filtered water. Divide volume of water filtered between backwash. Okay. So volume of filtered water used in backwash, rate of backwash multiply with duration of backwash multiply with area of each filter. You can get it. So how much volume of filtered water used in backwashing, because you need a separate tank for it too. So that area is also defined. So you can get it like this. So if you have a rate of backwashing, on what rate you are going to clean the filters, and then what is the duration of backwash? Suppose 5 to 6 minutes, 5 minutes or 10 minutes duration. And then how much area of each filter? Suppose 10 filters, so 10 multiply with the each area of each filter. So like this, you will get the volume of filtered water used in backwash. Now, volume of water filtered between backwash, that is both ratios you are going to calculate, no? Volume of water used in backwash upon volume of water filtered between backwash. So volume of water filtered between backwash, you can get it, rate of filtration that is given as a standard, into duration of filtration that is also given, multiply with area of each filter that you have determined. Like this, you will get both the parameters. You find out the ratios of both. This is a problem first for the rapid filtration. There's a capacity of water treatment plant 24 MLD. Rate of filtration is given 5 meter cube per hour per meter square. Area of filter bed is given length into width. 24 into 10 to the power of 3 divided by 24 divided by 5. So you can calculate it. Area of filter bed. Length is given and width is given. So that is, they have calculated in meters square. So you will get it 200 meters square. Length is equal to 1 meter Length is given 20 meter. Percentage filtered water for backwashing. I have not written the question. Just simply for the explanation purpose, I'm just explaining. The percentage filter water required for the backwashing, that formula is given. You can write it and you can get it. 6 into rate of filtration into 10 by 60. Then rate of filtration multiply with 24 minus 10 by 60. So 4.19% duration of backwash. So you can convert into liter per meter per second. Total surface area is required. You will get it Q divided by rate of filtration. It's only simple concept that these formulas you have to remember that. Only simple concept they can ask. They will not ask the whole question. Only one concept they can ask. Surface area of single filter. So total area 180 we have it. If you're going to provide 4 filters, then you will get the each area for single filter. So 45 meters square you have to provide for one filter. There are the four filters you are going to propose it. Okay. Yeah. Length divided by width ratio. So length is equal to 2L. Then L by B, you can get 2 by L. Like this, you can do the simple calculations. There's another question here. 2.5 mld plant. You convert into the meter cube per second, 0.029 meter cube per second. Rate of filtration is given 125 liter per meter square per minute. That also you convert into meter cube per second, meter cube per meter square per second. And total surface area you can calculate it. So how much capacity? 0.029 divided by total surface area. Q divided by rate of filtration. They have calculated based on this. You can calculate it. Okay. So there's one another thing. Percentage volume of water used for backwashing divided by volume of water filtered between backwashing, that we have calculated here. That also we can do it. Okay. Now we'll come for the design of slow sand filtration. The bacterial removal efficiency, as I told you, in particle removal efficiency is 98% to 99%. Rate of filtration is given for single meter tap will be the 100 to 200 liter per hour square. No pre-treatment of water is required. Post-treatment is optional. Coagulant is not allowed to pass through the slow sand filtration. If it is allowed to pass, a smaller particle in coagulated water grows inside the filter media, blocks it permanently, and causes operational problems. What are the components of slow sand filtration like rapid sand filtration? There will be the filter box, rectangle opens to the atmosphere, watertight tank, size of 100 to 2000 meter cube capacity. Bed slope should be 1 to 100, same as before, rapid sand filtration. There will be the filter media. These are all the components. Filter media, silica sands used as media. Thickness of this media you have to provide as 90 centimeter to 110 centimeter. Effective size of the sand you have to provide a D10 is equal to 0.2 to 0.35 mm particle size distribution of the grains. Uniform coefficient D60 by D10 should come in the range of 1.8 to 3. These are again the design parameters. Smaller the particle size, smaller the pore size, the higher area of contact is required in that case, and low rate of filtration will be there, and better quality of water you will get it. So the more smaller the particle size of the pore, you will get the better efficiency of we can say the cleaning treatment. There's a gravel bed, third thing. Gravel bed, as I told you, which supports the sand media. Thickness should be 30 centimeter to 75 centimeter. Size should be 3 mm to 60 mm for the well graded one. These are some things which we have to address. Does not permit sand particles to escape from the filter media. Then you have to provide an under drainage system like before. Open drainage system provided with lateral and central drainage. Inlet and outlet you have to provide it to supply water uniformly over the sand bed. Outlet to collect the filtered water at the constant rate. There's a piezometric head. You have to provide a piezometer to know the water level on the top of the sand bed. And then initial head losses, you have to detect it. Then head loss measurement also has to be done, like before in rapid sand filtration also you design. So head loss before starting of the filtration should be 10 centimeter to 15 centimeter in that range. When head loss reaches to a value of 70 centimeter to 90 centimeter, 90% of sand bed thickness It indicates that filter is not working at the rated capacity. It badly needs cleaning or washing. 10 to 15% head losses is okay. If it is increasing up to 70 to 80%, then means you have to replace the bat. So it's an indication. It's badly needed cleaning, and then cleaning required once in every 1 month of 3 months, 1 month to 3 months in a period, not every day. Top 1.5 to 3 centimeter of sand bed is scraped off every until depth of the sand bed gets reduced to 50 centimeter. Beyond this depth, coarser sand low filtration is found. So scraping of fine and washed with 0.2 to 0.6 of filtered water is required. Same for this 2 to 6% filtered water is required for wet washing. Here 0.2 to 0.6% filtered water is required. Scraping of fine sand was means what will happen on the top. There are the various layer. Top of the layer will be the sand layer. You have to complete because a lot of bacteria will be clogged in the pores. So rather than removing these bacteria is difficult, you just replace the sand itself from the top. So that is they are saying. So design of SSF, first rate of filtration you have to identify. Superficial velocity, total area of suspension filtration also you have to identify, and Q divided by ROF, the same thing. Fixed size of each filters, you have to fix the size of each filter. Suppose 5 filter, 6 filter, you are going to take it. Length and width for each filter you have to determine it. Find the number of filters or fix the number of filters, and find the size of each filters length and width based on the length and width of the relations, and provide one extra filters for the reliability conditions. Suppose you have fixed 12 filters in the unit, then you have to provide one extra filter for the reliability conditions and for the standby operations. This is one example here. Rate of filtration is given 180 liter per hour per meter square for slow sand filtration. Population is 50,000 persons. Per capita demand is given 150 LPCD. Maximum demand is equal to 1.8. That you know this relation, 1.8 of the average demand, 180% of the average demand. Maximum demand you will calculate for the water supply. 180% of the maximum demand is given. As it would be 6 minus 5. So total filters you have provided 6. So first you will determine the total quantity of water that is required, that is to be treated. So population multiply with per capita demand, 50,000 multiply with 150 liter per day. You will convert into meter cube per second. You will get a flow rate. Design demand, wherever you are going to design a water treatment plant, you have to design on a maximum conditions. So maximum demand is equal to 1.8 of the 180% of the total water demand that you got it. So 1.8 multiply with Q, 1.8 into 50,000 into 150. You will solve it. You will get the sum answer for the maximum demand. Now total area of slow sand filtration required 1.8 into Q design divided by ROF. This same total surface area required will be Q divided by ROF. So Q you already got it, that Q1, and if you divide with rate of filtration that is given 180 liter per hour per meter square, you will get 3125 meter square area, total area for the slow sand filtration. As I told you, for SSF required a larger area. So N is equal to number of 5 filters are in operation, one will be in the standby mode, and then total area will be getting like this. Total area of each filters, total area of how much you are getting, 3125. If we divide with 5, you will get 625 meters square area for each filter allotted. Yeah. Then size slow sand filters required to treat 10 mld water with RDF. If there is 10 mld water that is need to be treated, how much mld they are getting it? You solve it to 7.5. Okay. RDF. This is another question. Find how many number of 20 to 10 size slow sand filter required to treat 10 mld water with the rate of filtration rate, or ROF, it is 200 liter per hour per meter square. So you can get it in the same way. The total area required for the filters Q divided by ROF. First you get the Q value, and then total size, number of filter size they have given 20 into 10. The 10 into 20 you can get it, and you can convert into a respective unit. And the number of filters required are 11. Like this is all. Now head losses are also play a very important role while we are talking about the filtration, maybe the slow send filtration as well as the rapid send filtration. For identifying the head losses, there are some two empirical relations that we use to take care. Generally, they don't ask. If they ask, it's up to you. If you are able to solve with the higher efficiency, you can solve it. So head losses during filtration, there's some standard formulas that you have to take care. Okay. So you can note down, or I will circulate this PPT. You just take it. How to solve this? These numericals also I will circulate with you. So there's one equation called as Karmin-Konchny equation for the head losses for the filtration. So HF will be F into Z into V square multiply with 1 minus N divided by N to the power Q divided by Z into D. Z is the depth of sand bed, the gravel bed that you have provided. Z is a normal gravity constant. D is the diameter of the particle. And F will be 150 into 1 minus N divided by RE. RE is the Reynolds number plus 1.75. RE you already know, rho Vd by mu, Reynolds number for laminar and turbulent flow. And Xi is equal to V into D into Xi by gamma. Particles are assumed to be spherical. This Xi sign is used to denote the variation from the sphericity, and V is the spherical velocity, which will be equal to rate of filtration. N is the porosity of the sand, and D is the diameter of the sand grain, small d. And this equation is valid only for a particular porosity. At time increases, porosity and velocity decreases. So this is rarely used equation. Okay. So head loss during backwashing, this is the equation they use to do it for the calculations. Head loss during backwashing, B is in a subscript. So Z into 1 minus N is equal to 1 minus 1 loss into settling velocity will get formula. The rate Z will be integration. So they keep asking sometimes, generally they don't ask, so don't go into details. Particle removal efficiency, this is very important. We call as Iwasaki and Isaku equations. That is important. So if sometimes they ask the particle removal efficiency, you have to apply this formula only. C naught minus CT divided by C naught multiplied with 100. The uniformity constant that you have to measure, no, the same thing. So here we have done it. The integration, if you do it for this equation, if you will go for the dc by dz will be directly proportional to c, so you can write it as dc by dz is equal to minus lambda c. C is the integrate constant and lambda is a constant for integration, and then c is already given. So integrate between the limit ct to c naught and 0 to z naught. So you can go for the 1 degree integration, simple integration in terms of limits. Left hand side, right hand side, left hand side you can put the limit ct to c naught, and right hand side 0 to z, and you separate the parameters z and c here. So they have done it. After solving this, after integrating one-time integration with respect to this limit, if you integrate this equation, you will get this result. ln of login of ct by c naught is equal to 1 upon z. Ln of c naught by c net ct. Lambda is the filtered constant that you have taken, and then you can write it in that form also. C naught divided by ct is equal to 100 divided by 100 minus eta, and eta is the efficiency for the removal efficiency. And finally they have solved it. Filtered coefficient lambda is equal to 1 upon z into ln of the 100 divided by 1 minus eta. Question number 1. This thing you can remember it. HF, the Karman-Konzi equation head loss will be directly proportional to V square, and this will be inversely proportional to TH, temperature coefficient. What are the operational problems associated with the rapid send filtration? These are the problems that also we have to address. One is the cracking and clogging of filters. Yeah. So filter troubles, cracking and clogging of filter bed. There's one problem. Second is the formation of mud balls because of inadequate wet washing, ear binding sometimes. If there is a negative pressure head generated in the filter, which is greater than 1.2 meter, then ear binding, then sand incrustation, jetting in sand boils, and sand leakages. Cracking and logging of filters. It's a surface clogging and cracking are usually caused by rapid accumulation of the solids on the top surface of the fine media, and the compression and shrinkage of soft gelatinous coatings on the sand grains tends to form cracks on the top of the filter layer as the head loss increases, and these cracks are more prominent near the wall junctions. The effect of such cracks is to permit the dirty matter to penetrate into the filtered media and causes a problem. So washing is required for this. Second, as I told you, the formation of mud balls. Mud balls are, we can say, the coagulated turbidity flocks, sands and other branches, and are formed near the top layer of the filter media. Mud balls are caused due to the insufficient washing of sand grains. They are not going to clean it properly. Mud may accumulate on the sand surface to form a dense mat, and it creates a layer actually sometimes. During wash, there may be some lateral pressure between the point where the water breaks through and the sticky mud is pushed into the lump or ball of the size of the pea up to 2 to 5 centimeters or more in diameter. So a 50% expansion of sand in washing is effective in minimizing the production of mud balls. Formation of mud balls can be eliminated, reduced by providing an adequate backwash of the filter media and providing a disinfection of the filter media. These areas occupy the void space of the filter media drainage system. Trouble is especially likely to occur if the water is saturated or supersaturated with air in solution. The separation of these dissolved air may be difficult due to the following reasons: the negative head pressure due to the excessive loss of head, increase of temperature of water as it passes through the filter media. These are the problems. A release of oxygen by algae also. Air binding can be minimized. Number first, by avoidance of excessive negative head by providing a water depth of at least 1.5 meter above the surface of unexposed filter bed area. Then sand incrustation. It may occur either due to the deposition of sticky gelatinous materials from the influent water or due to an after crystallization of calcium carbonate in case of sand grain in Las. This is the reason for it. So sodium hexametaphosphate may also use for the small plants to keep calcium carbonate in dissolved state. So you can remove that. Then next one is the jetting in sand boils. Jetting in sand boils results during the backwashing when backwash water follows path of least resistance and in porosity and permeability of the sand and gravels. When jetting becomes severe and the sand boils up like quicksands and gravel as well as the sand are lifted to the surface, the tendency of jetting can be minimized by surface moss or air scoring that I told you as a backwashing in advance of bad fluidization. So it can also be eliminated by use of 8 centimeter layer of coarse garnet or we can say the ilmenite between the fine media and gravel media. And then sand leakage is last one. It's a downward migration actually for the sand leakages. An escape of fines results when layer of the smallest gravels are displaced during the backwashing. Okay. How to assess the performance? This is the head loss that we are talking. The performance will be assessed based on the turbidity, based on the color, based on the iron and magnesium present in the water, and taste and odor present in the water. So based on this, the efficiency, yeah, we can say the performance of a repeat filtration and fluorescent filtration will be assessed. So you have to check the turbidity and NTU. If the turbidity is, if the influent water does not have a turbidity more than 30 to 40 ppm, the filter can reduce the turbidity to less than 1 ppm. Influent means the water which is coming out after primary treatment from the sedimentation from clarification process. And effluent will be this one, treated after filtering, after filtration. So influent turbidity you have to check it, and effluent turbidity you have to check it. If here the turbidity is 30 to 40 ppm, if here the turbidity is 1 ppm to 2 ppm, means efficiency of filtration is very good. So like this you can check it. Color also with a visible identification you can check it. Iron and magnesium, rapid filters remove oxidized or oxidizing ions, so it is less efficient in removing manganese. So some portion of manganese iron can be removed. Taste and odor also, through this you can identify it like this and go for it. This is one example is given for the pressure filters, how to design a pressure. Like before, for the, as we have discussed about the rapid filtration, source filtration, like this also we have to take some standard parameters. So removal efficiency should be 60 to 70% for it. Rate of filtration should be, you have to take 6,000 to 15,000 liter per hour per meter square. And pressure should be in a pressure filter where the filtration can under the pressure head to 30 meter to 70 meter pressure head you have to maintain, means 300 to 700 kilonewton per meter square pressure head you have to maintain in the pressure filter. Pressure filters are widely used in swimming pools, industries, and private buildings. And then diameter of the particles should take in that way, that much, and coefficient of uniformity you have to take 1.2. Surface area of the filters you have to take pi 4 into d square, like Q divided by ROF, the same process. If it's a dual media filter, it's a single media filter, based on this also you have to check it. Okay, so these are the things for the, this is one operations for the slow filtration, how the things are happening. So like this the filtration has been completed, and yeah. Yeah, few people are there all. Yeah, okay. So I will be moving for this
Yes,
part. So we'll try to cover this disinfection theory as well as the water distribution network today. Effluent discharge, anyway, we have covered in our regular classes, the sludge disposal, and those sludge disposal I will be covering here. But the series of effluent discharge in land treatment and dilutions, natural purification process, natural purification methods, right? Dilution curve, these things, BOSEC curve that we have, DOSEC curve and all that we have discussed in our regular classes. Anyway, here also from the competitive point of view, I will discuss. Okay, so no problem. So we'll go for the disinfection first. Um, I will save this PPT to you, so you can, once you have a time, because we have a time constraint, later on you can read properly and you can do some numericals on this. I think the numerical part also I have shared in the GATE classes. You can see that, and the solution is given over there. There's a time limit over there, and you just solve it. So we'll move for the disinfection part. The objective is clear: to kill the germs, bacteria, pathogens, viruses present in a water or maybe in a wastewater, and to protect the water against future possible potential contamination also, we have to make water free from the pathogens, not through the, suppose sometimes what will happen, water is free from pathogens, bacteria and biological growth today itself, but with the course of time, if it is traveling in a distribution network, or if it will be stagnant in a water storage reservoir somewhere, the bacterial growth can again, we can say, the grow in that. So we have to protect this water against future possible potential contamination also. So that's why residual chlorine you are going to dissolve in a water for after treatment. Okay, so the function is clear. It is carried out to eliminate or reduce to a safe minimum limit the remaining microorganism and to prevent the contamination of water during its transit from the treatment plant and to the place of consumption. Disease causing pathogens killings. Either we are killing the bacteria, or we are inactive those bacteria. Okay. So the common process, disinfection can be done through the chlorine only, with chlorine, and disinfection with the chloramine. I will go for the reactions, how the chloramine will be happening and how it will kill the bacteria and viruses. So chlorination is the very common process for it. So what is chlorination? It is the process of adding chlorine to the drinking water to disinfect it and kill the germs. Different processes can be used to achieve safe levels of chlorine in drinking water. Chlorine is available as compressed elemental gas like sodium hypochlorite, NaOCl. So chlorine is available as a compressed elemental gas as a sodium hypochlorite solution, or we can say or we have a sodium calcium hypochlorite solution. Okay, so it's there available in the market, and chlorine is not available in a free form. Still available in a sodium hypochlorite solution or maybe a calcium hypochlorite form. Okay. What is disinfectant? We use the disinfectant, as I told you, we are using alum. I'll go in details one by one. Okay. Alum is a coagulant, not a here we are using these things, chloramines and all that, calcium hypochloride, and a sodium hypochlorite solution for as a disinfectant. Substance used to carry out the disinfections are called as a disinfectant. A requirement of an ideal disinfectant: it should be effective and efficient killing, faster rate of killing, should be toxic only for organism, not for the human, should have enough residual power, should be of such nature that it can be easily detected from the water. So these are the characteristics it should have. Whatever the disinfectant you are going to choose, it you have to choose based on these parameters. Okay. So mechanism of disinfection, it will work in four mechanisms: by damaging the cell wall first, and by attention of cell wall permanently, and then by damaging the protoplasm, and by precipitating the enzymes, nutrients, etc., and by disposing the waste products. There are three methods of disinfection. We'll start from the two methods we will discuss. There's a physical method, and their second one is the chemical method. Number physical methods, How to disinfect water? Just boiling. First is the by heat, by applying heat energy, by using heat energy. So boiling is very most commonly used operation for disinfecting water, right? On a high temperature, very high temperature, if you are boiling water, of course the bacteria will not, and viruses and these pathogens will not survive on a very high temperature. Okay, so you boiling is physical operation using light energy like a UV rays, ultraviolet rays. That is through the UV action also you can disinfectant water. And then what are the physical disinfectant? Ultraviolet light, very good and effective disinfectant, UV rays. Electronic radiations also can be used. Gamma rays also can be used. Even a sounds and heat also you can use it as a physical method of disinfection. And what are the chemical methods? Using excess lime, using surfactant, using metal ions, using potassium permanganate means KMNO4, and then ozonation is very effective. We'll talk about the ozonation in details, how the ozonation will be so effective in water treatment. And then halogen group of chemicals like iodine, bromine, as well as the chlorine. What are the chemical disinfectant that we are going to use it? Chlorine dioxide, hypochlorite OCl negative, ozone O3, halogens like as I told you bromine, iodine, yeah, iodine I, and then bromine chloride, metals like copper and silver treatment of water, copper treatment of water. You must have seen the copper treatment like it's RO combined with the copper treatment, RO combined with the silver treatment like this. You must have heard in the water purifier. The same way, so copper and silver also play a very important role. It's very good disinfectant. And then potassium magnesium, potassium as I told you, potassium permanganate as I told you. And phenols also can be used. Alcohols, ether can be used as a disinfectant nowadays in sanitizer, like ethanol you are going to use it. Soap and detergents also can be used as a disinfectant. Ammonium salts also you can use it. These are all the chemical disinfectants. Hydrogen peroxide H2O2 is also very good disinfectant. Several acids and bases are also work as a disinfectant. So there's a very strong, very for the chemical disinfectant. Okay. Minor method of disinfection, as I told you, boiling is very common method. In terms of destroying the organism, best method is and no residual power economical for the large scale purposes. UV treatment, UV rays of wavelength through 40 to 260 nanometer acts as a powerful disinfectant. Instant killing, effective and efficient killings, damage the protoplasm, and no secondary problems for any amount of UV exposure. No much space required for UV treatment, so it is very effective. And then this formula you note down, log in our ln of the nt divided by n naught is equal to minus k into I into t. Nt is the number of organisms remain in the water after the exposure. T is the no initial number of organisms. K is the disinfectant rate constant. I is the intensity of UV radiation, that will be microwatt per centimeter square, and T is the time of exposure. So how the UV radiation will be taking place in a water treatment for the disinfection, this equation will be followed in exponential manner. These are the units you have to take it, right? To reduce the microorganism in water from 10 to the power 6 to 100 in 2 minutes, what intensity of UV radiation is required if K is equal to 0.006 centimeter per microwatt into second. So if you want to solve this numerical, you have to apply this equation. Ln divided by n divided by nt, nt divided by n naught, and then you can get the single answer. So sometimes they ask, if they are asking, you have to apply it directly the formula and you will get the answer. So we will get the I value is 12.79 microwatt per centimeter square. Excess lime treatment is also very work as a good treatment for this infection. Growth of microorganism is influenced by pH level. If pH is greater than 9.4, growth of microorganism is almost zero. And the highly alkaline nature, bacteria and viruses cannot survive. So if it's greater than 9.4, means microorganism will be to water. And lime is also increase its pH level, and adding water increases pH more than 9.4. Recarbonation is required to dissolve precipitate to dissolve the precipitates. formed as a result of lime treatment, which is expensive. So as I told you, this recarbonation is a process for removing the hardness. The same way it can be followed here also. So through the recarbonation also, the pH level can be increased. These are the various methods, minor methods. If the pH level is equal to 7, so decreasing the pH, increasing the acidity, and leading to the corrosion, the growth of microorganism will be optimum as pH 7 level. The component of disinfection, there is a primary disinfection and secondary disinfection. What are the primary disinfection process? An activation of microorganisms present in water. This is the first process while you are using particular disinfectant for disinfection purpose in the water. So two processes will be happening: primary disinfection process and secondary disinfection process. In a primary means first inactivation will happen of microorganisms. Secondary, maintaining disinfecting residuals in a distribution network and distribution system. The surfactant, if you talk, surfactant means surface active chemical substances you have to use as like soap, detergents, phenols. Quality of water will be affected while you are using surfactant as a disinfectant. Treatment with metal ions like silver and copper, as I told you, used to carry out the disinfection, no residual power required. Electrocatadions, treatment of water with silver can be done through this process. DC current required, electrode coated with the silver is required nowadays in RO systems and water purifier. This mechanism is followed. Treatment with the KMNO4, well in rural areas as disinfected with KMNO4. Disinfection is slow and takes 24 to 48 hours. If you belong from villages, in a rainy season, the government PhD department, they used to provide KMNO4 powdered form, and they put it in a water bodies like well and all that. So it's a very good disinfectant, potassium permanganate, and after 24 to 48 hours, water will be completely disinfectant, free from pathogens and bacteria, and their water will be smelly for few days. If you are drinking these, I belong from villages, then we were dependent earlier on well only. So we used to put this potassium permanganate in water. That's why I know this taste. Okay. So when reacting with organism, pink color is formed. If you have seen that, once you dissolve this KMNO4, of course, dosage should be defined. If you put it in, generally they put it just like that, and this pink color is formed, which takes 24 to 48 hours to disappear, and it's very cheap method for disinfecting the surface bodies. So how the chlorination will work? Yeah. So first you have to understand the various form of chlorine. There is a free chlorine, combined chlorine, chlorine dioxide, and all that. And where the chlorine residual is required, what is the combined chlorine, right? These definitions, it should be clear for you, right? So as I told you, chlorine kills bacteria in the water. It's a common theory. Enzymatic hypothesis, according to this chlorine compound formed when chlorine is added to the water, interface with the certain enzymes involved are created within the cell plasma, and hence action of disinfection proceed in two stages. Number first is penetration of cell wall by the disinfectant, number one. Number second, it reacts with the enzymes also. So like this, in two stages, chlorine work as a disinfectant. When chlorine is dissolved in a water at temperature between 49 to 212 Fahrenheit, it reacts to form a hypochlorous acid and hydrochloric acid. If you have seen I will show you the chemical reactions. So there's the hypochlorous acid forms, and then there is a hydrochloric acid forms within few seconds. So Cl2 will react with H2 molecules in water, and then HOCl and HCl will form. These both are acids, hydrochloride acid as well as the hypochlorite acid. This process is called as a hydrolysis. And this hypochlorite chlorous acid HOCl negative, it's a negatively charged, ionizes or dissociated with hydrogen into hydrogen, that is H positive molecules, and then hypochlor which called as so IOCl can break as positive plus OCl. OCl negative work as a disinfectant. Is taking place. It is the hypochlorous acid. This OCl negative is the hypochlorous acid, and hypochlorite ions, which accomplish the disinfection process. So when the chlorine is added to the water, all the three elements, elemental chlorines and hypochlorous acid and hypochlorite ions are formed, and they remain at equilibrium at different concentrations depend upon the pH of the water. So like this, the three acids will form there, and then like this, the disinfection will be completed. Then all the reactions will be completed, like both the hydrolysis process as well as the ionization. Both the processes will be taking place simultaneously. What is free chlorine? The chlorine existing in water as a hypochlorous acid, hypochloride ion, and molecular chlorine is defined as the free chlorine. Once the process is completed, if the excess chlorine is remaining, that chlorine is called as a free chlorine. And the disinfecting efficiency depend on the various parameter. The ratio of hypochlorous acid to the hypochlorite ion being greater at higher ratios. If pH is less than 5, chlorine exists as elemental or molecular chlorine. At pH between 5 to 10, it remains in both the forms, hypochlorous acids and hypochlorite ions. At pH greater than 10, only hypochlorite ion exists. So these are three elements, as I told you, elemental chlorine, hypochlorous acids, and hypochlorite ion. Because of the hydrolysis process and ionization process, both the acids will form. And pH play a very important role, as we have discussed. More the pH value, the bacterial will not survive in the more pH greater than 9. If the pH equal to 7, the optimum rate of bacterial growth will happen. pH is less means the more chances for growing of the bacteria. Since the hypochlorous acid is about 80% times as effective as the hypochlorite ion, this has to be noted down. The hypochlorous acid is 80% effective as the hypochlorite ions. The pH of water should be maintained as less than 7 to prevent the great ionization of HOCl. So hypochlorite salt also ionized in the water. So suppose this is the calcium hypochlorite will react with the H2O, then HOCl will be formed, then COH voltage will be in the form of precipitate and sludge. And if you are using a sodium hypochlorite, then H2O, it will the same reaction will be happening. In both the cases, as I told you, the raw product you can take it as a calcium hypochlorite, or you can take it as a sodium hypochlorite. And both the reactions will be taking place. It will be in the precipitated form, and HOCl will be formed. And HOCl work as a disinfectant. HOCl means hypochlorous acid. What is chlorine demand? The amount of chlorine consumed in the oxidation of these impurities before any disinfection is achieved is known as a chlorine demand. So after the chlorine demand is fulfilled, chlorine will appear as a free available residual chlorine. The free available residual chlorine will then serve as a disinfectant to kill the pathogens present in the water. So it is essential to provide sufficient time and sufficient doses of chlorine to satisfy the various chemicals reactions and leave some amount of untreated chlorine as a residual chlorine for the disinfection of the water. So chlorine demand is therefore the difference between the amount of chlorine added to the water and the quantity of free available chlorine remaining at the end of the specified contact time, contact period. So chlorine demand would be how much chlorine you have added minus how much free available chlorine is there, then the chlorine demand you will get. These are the form of application of chlorine. Some forms like bleaching powder, you can use it for the chlorine addition, and calcium hypochlorite commonly use it. Calcium hypochlorite is having a 36% or 33.5% roughly of available chlorine. So sometimes, most of the cases, calcium hypochlorite they use it in terms of powders form in solid forms as a chlorinated agent for the disinfection purpose, for the pre-chlorination as well as the post-chlorination purpose. If I'm going for the chloramines, that is also very effective compound of ammonia and chlorine that also can be used as a free chlorine compound. And then chlorine dioxide, you can take it from it. So these are the various forms are available for the in the market. To the calcium hypochlorite, can go for the discuss hypochlorite. So these are easily available materials. in the market, you can take it and we can use it as a disinfectant. And the chloramine is also very good. It's a addition. It's a mixture of ammonia and chlorine. So free chlorine can be extracted. Now the chlorine doses are playing very important role. Excess doses make the water highly, we can say, the poisonous, and it should not be fit for the drinking. So doses has to be decided carefully. Okay. It depends upon the organic matter present in a water to be disinfectant, pH of water, and amount of carbon dioxide present in a water, temperature, and time of contact. So while you are deciding the chlorine doses, it depends on the organic matter present in a water and pH of the water. You have to check it, and the amount of carbon dioxide present in a water, or of course the contact time. What should be the time duration for the chlorine doses? 5 minutes, 10 minutes, 20 minutes, 30 minutes, that we have to decide it. And temperature also play very important doses while the chlorine doses we are going to decide it. So there's suppose one question they are asking for the chlorine demand. They calculate the quantity of bleaching powder required per day for disinfecting 4 million liter water per day, 4 mld water. The dose of chlorine has per day for disinfecting to be 0.5 ppm, and the bleaching powder contains 30% of available chlorine. If it is not given, you consider as 33.5% of available chlorine in bleaching powder. As I mentioned here, no, uh, the calcium hypochlorite contains 33.5% of available chlorine. Calcium hypochlorite is nothing but it's a bleaching powder only. So, and the bleaching powder 30% of available chlorine, and chlorine required at, as you can solve it, chlorine required at 0.5 ppm. So 0.5 ppm multiply with what is the total amount of water, quantity of water, 4 million liter per day. So 0.5 into 4 into 10 to the power 6 divided by 6, you will get it as 2 kg. Million liter water per day, you convert into the kg. Finally, you will get it how much chlorine is required, that is 2 kg is required for the whole amount of water for disinfecting. So bleaching powder contains 30% of chlorine amount of bleaching powder. So you can, that percentage also you can calculate it. So 2 kg into 100 divided by 30. So you will get a 6.67 kg of bleaching powder total. So you have to purchase a 6.67 kg of bleaching powder from the market, in which 2 kg of the chlorine will be available. Is required for disinfecting a 4 million liter of water per day. So every day 2 kg of chlorine is required. So chlorine doses and chlorine amount you can determine it. Chlorine using in the treatment of, this is another question, chlorine using in the treatment of 25,000 meter cube per day is 9 kg per day. The residual chlorine after 10 minutes contact period is 0.2 mg per liter. Calculate the doses in mg per liter and chlorine demand of the water. So water treated per day, you can calculate it. Liter per day, you can convert million liter per day into the liter per day. So meter cube per day it is given, you can convert in liter per day. Chlorine consumed per day, it has given it's 9 kg. So 9 into 10 to the power 6, you will get it in mg per day. Chlorine used per liter of water, so 9 into 10 to the power 6, and then per liter of water you can calculate it based on this, divide by 25 and 10 to the power 6, then you will get 0.36 mg per liter doses has to be required for the disinfectant purpose. And residual chlorine is given as 0.2. The residual chlorine after 10-minute contact period is 0.2 mg per liter is given. So what is chlorine demand? You can get it. Chlorine demand will be the total chlorine used, chlorine added, minus the residual chlorine. You will get the chlorine demand. Simple questions will be coming. Okay. Now, how the chlorine will be used, in which form, and what stages it is used. So there are the seven stages of form of chlorination. We call as the forms of chlorination. How the chlorine will be added on various stages. Suppose if I'm talking about the water treatment plant, we have a pre-chlorination, then we have a post-chlorination, right? 2 times we are going to add it. So like this, there's the forms of chlorination. What are the forms of chlorination? Plain chlorination, dechlorination, dichlorination, So we have explained here plain chlorination, chlorination and all that. Just I will not waste too much of time. You will be having a document, you will be having notes and PPT. We just go through that, okay? But doses you have to remind it how much it is required. Suppose if I'm talking about the plain chlorination, raw water as it is entered to the distribution system in tanks or reservoir application also to check the growth of weeds and organic matter and algae and bacteria present in the water. Also removes color and odor from the water. The plain chlorination to the untreated water is required. It is restored to when water is relatively clear with the turbidity less than 20 to 30 ppm. So normal doses should recommended 0.1 to 1 ppm for the plain chlorination. So if the complete treatment is not there somewhere, if the turbidity is not too much of high, then you can go for the plain, just disinfectant only. Plain chlorination you can provide it by using the doses 0.125 to 1 ppm. Then second is the pre-chlorination. When the chlorine is added to the raw water before any treatment, it is known as the pre-chlorination, as I told you. Under pre-chlorination, chlorine is added before raw water enters into the sedimentation tank. Before sedimentation and filtration, chlorine is added. This helps in reducing the coagulant required for oxidation of organic matter. Dosage should be 0.1 to 0.5 ppm. Reduces the bacterial load on the filters. It helps maintaining longer life units. It controls the algae and plankton in the basin and filters. It eliminates taste and odor. It prevents putrefaction of sludge in the settling basin. There are the various advantages for the pre-chlorination and the water treatment. Okay, the dosage should be 0.1 to 0.5. Chlorine residuals to maintain 0.3 to 0.4 mg per liter free available chlorine throughout the treatment. Normal pH values, the free available residuals at the effluent should be 0.2 to 0.3 mg per liter. At higher pH, which is 8 to 9, the doses should increase. Free residual chlorine to complete the bacterial kill within the 10 minutes contact time period. At least 10 minutes are required to kill the bacteria. So this the contact period is required for it. 0.4 mg per liter doses are recommended. For 30 minutes contact period time, 0.2 to 0.3 mg per liter is required. So these are the various doses they have given it. All the doses are coming less than 1 ppm only. Maybe the free residual, maybe the chlorine residuals. Okay. Suppose for inactivation of Christoph E higher doses, this is a particular type of microorganism, is required as 0.5 mg per liter. And this is the highest doses. Okay. Now this is the post chlorination. After filtration chamber, we have to send the water for the chlorination. That is actually post chlorination. So post chlorination indicates the application of chlorine to water after all the treatment of purification of water are completed. This is a standard form of chlorination in which the chlorine is added to water as it leaves filters and before it enters to the distribution systems. You already know about the water treatment plant post chlorination. Doses कितना होना है? To leave a residual chlorine of 0.1 to 0.2 mg per liter after a contact period of 20 to 30 minutes. This residual chlorine will ensure the disinfection of water if at all any recontamination occurs in the transmission distribution system. These questions are a descriptive types of questions are also coming this time in GATE. That's why I'm reading those things. Sometimes there's some statements will be giving false and correct statements and multiple statements where they can ask which are the following statements are correct. Suppose first and two, second and third, like this. And one is given a reason, another one will be given a impact for it, whether both are matching or not. First and true, second is true, first is dependent on second is dependent on first. Like this questions will be coming descriptive type. So for that, this understanding you have to be here. If you have that understanding for post chlorination and all that, then you can easily approach the answers. Okay, so that's why it is very important to read each and every point. Chlorine doses should not be generally greater than 2 mg per liter, as the excess residual concentration of chlorine may damage the pipelines and pump impellers. Pre-chlorination is always followed by post-chlorination. So next is double chlorination method, multiple point multiple points. They So you can say here refers to the application of chlorine to water at 2 or more points in the purification process. When raw water is highly contaminated and contains large amount of bacterial life, it becomes necessary to adopt double chlorination. Okay, so we don't have that much of time. That's why we are going a little bit fast. There's a breakpoint chlorination. I will explain the breakpoint chlorination. It is very important part. So you see this diagram here. This is very important chlorination part. Stage first, stage second, stage third, and stage four. This is the saturation stage actually. After that, the excess chlorine is not required. So this breakpoint chlorination is the point where the maximum amount of chlorine is added, and after that, more oxidation will not take place. Suppose oxidation of iron, manganese, nitrate, sulfides, and organic matter present in the water in first stage. First stage. Second is the formation of chloramines and chloroorganic compounds, which will be responsible for killing the bacteria and microorganisms. Second stage, third will be the destruction of chloramines and chloroorganic compounds. And stage four is the formation of free chlorine in presence of chloroorganic compounds. This is not destroyed. Okay. When chlorine is added to the water, there are the following two actions takes place. It kills the bacteria present in the water. Thus, the disinfection is accomplished. Number second, it oxidizes the organic matter present in the water. Like chlorine demand is satisfied. If water has no chlorine demand, any chlorine added to such water will appear as a residual chlorine. Hence, the relation between the applied and residual chlorine will be indicated by a line. This is the graph. Residual chlorine on y-axis and applied chlorine on x-axis. 0, 1, 2, 3, 4. You must have done in your environmental engineering laboratory the residual chlorine demand. So this is the breakpoint chlorination point where the residual chlorine amount will reduce up to the certain limit. So what is happening here? Having a slope of 45 degree as shown in figure, which shows the relationship between the applied and residual chlorine. This portion, how much is applied and how much is residual. The sudden decrease in the residual chlorine is due to the fact that the increased concentration of applied chlorine break down the chloramines by changing them to nitrogen compound, thus reducing the residual chlorine, and also a lot of applied chlorine is utilized in oxidation of the organic matter present in a water. This represents stage third, which is sometimes accompanied by bad smell and taste. During the stage third, the relationship between the applied and residual chlorine is represented by the curve CD. At the point D, the bad smell and taste suddenly disappear, and the oxidation of organic matter is also complete. So the breakpoint chlorination is nothing but it's a satisfactory demand where the saturation stage takes place for the oxidation, and further oxidation will not take place. And then chloramines is also break in its residual chlorine components. As I told you here, with increase in applied chlorine, there is a sudden decrease in the residual chlorines, and the chloramine will break in two parts. Okay. Uh, yeah. Further at point D, the residual chlorine has its maximum value, which reveals that true residual free chlorine, since the chlorine demand has been satisfied, and a further increase in the applied chlorine beyond point D result in an increase in the residual chlorine as represented by line E, the slope of which will be 45 degree because the entire applied chlorine will apply as a residual chlorine. This represents stage 4. So you see there, this is the chlorine residuals, this is the chlorine doses, chlorine rates with reduced materials, iron, manganese, H2S, and organics in NS3, breakpoint chlorination. The destruction of chlorine residual by reducing compounds and formation of chloramines and the chloroorganic compounds. And destruction will happen for the chloramines and chloroorganics here. And the formation of free chlorine and residual chlorine here presents chloroorganic compounds not destroyed. Here the free chlorine will be available. And then this is the indication actually how much chlorine is added. Based on this, you will decide this. So point D on the curve is known as a breakpoint chlorination because any chlorine that is added to the water beyond this point the water and appears as a water may be defined as So these are the following advantages. It will remove the taste and odor. It will have adequate bacterial effect. It will leave desired chlorine residuals. It will complete the oxidation of ammonia and other compounds. It will remove manganese also. Yeah. Then we have a superchlorination. The doses will be higher for the superchlorination, 5 to 15 mg per liter. If water is highly contaminated with bacteria and microorganisms, then superchlorination is required. The time is also will be larger, 30 to 60-minute contact period you have to provide for it. And doses will be higher for the superchlorination. Special cases we have to recommend for it. If water is highly polluted during the pandemic season, epidemic period of waterborne diseases, then we have to go for the superchlorination. Okay. The huge quantity of chlorine is dissolved and added in a superchlorination process. Dechlorination is just if there is an excess amount of chlorine is present in water, then for removing the chlorine, excess amount of free chlorine, residual chlorine present in the water is called as dechlorination. So dechlorination means removing the chlorine from the water. This is generally required when the superchlorination has been practiced. So generally both the process will be together, superchlorination followed with the dechlorination. So dechlorination process may either be carried out to such an extent that the sufficient residual chlorine of 0.1 to 0.2 mg per liter is present. So then dechlorination is required. The common dechlorinating agents are sulfur dioxide gases, activated carbon, sodium thiosulfate, sodium metasulfates, and ammonia. Okay. Following ideal conditions are assumed for the kinematics of chemical disinfection. This is we have done it actually, but this is there's the most of the numericals will be asked in that only, kinematics of chemical disinfection. So I'm just going through that, not in a detail. Yeah. You see that kinematics of chemical disinfection. So all cells of single species of organism are discrete units which are equally susceptible to a single species of disinfectant. Both cells as well as the disinfectant are uniformly dispersed in the water. During period of contact, the disinfectant stay unchanged in the chemical composition and constant concentration. Water contains no interfacing substances. So this is the time of contact. This is the Chick's law of disinfection under ideal conditions. So exposed cell contains a single active center vulnerable to a single unit of disinfection. Chick's law states that the number of organisms Y destroyed in a unit time is proportional to the number of organisms N remaining. So in form of differentiation, you can write it dy by dt is equal to k into n. And k, you can write it further, n is equal to n naught minus y. N naught is the number of organisms initially present. Y is the number of organisms remaining at any time, t. So you can write it as the n is equal to n naught minus y. And coefficient of proportionality. Coefficient of proportionality is equal to rate constant with dimensions 1 upon t. You can write in a much simpler way. You can integrate this equation dy by n naught minus y. You can take it in that side, right hand side, left hand side, and then you can integrate with 0 to t. So k into dt, one side, and this portion will be another side, and you can integrate between the limit 0 to y and 0 to t here, and then you will get the final exposure equation here. So finally, you can get it n divided by n naught is equal to exponential of the minus kt, where t is equal to 0, then n divided by n naught is equal to 1, 100%. At kt is equal to 1, n divided by n naught will be equal to, these are all the mathematical things. Okay, the rate of kill rather than being constant may increase or decrease with time. The rate of kill of organism may be expressed. So this kinematics will show you what is the rate of disinfection, what is the rate of killing the organism actually. In exponential manner it will be happening, and what will be the exact rate, how the disinfectant is killing the bacteria. So this is the equation. If m is less than 1, the rate of kill will decrease with the time. If m is greater than 1, rate of kill will increase the time. Actually, we have a time constraint, time is limited, that's why I'm just going a little bit fast. To second fact we have here that concentration of disinfectant will give this by using this equation, c to the power n into TP, T to the power n is equal to constant. So C is the time required to effect a constant percentage of kill of organism. N is the coefficient of dilution, which is a measure of the order of reaction. N is greater than 1. Efficiency of disinfectant decreases rapidly as it is diluted. If N is less than 1, then time of contact is more important than doses. If N is equal to 1, then concentration and time are of the equal weightage, and its first order reactions may be in the process. The examples are chlorine and 99% kills are. So these are the equations, two equations you have to use it. One is this one is this equation, and second one is this equation. So suppose C to the power 0.86 into TP is equal to 0.24. For E. coli bacteria, this equation will be valid. And then for this is the coccivirus for A2 grade. For this equation will be valid. These are standard experimental things. Okay, not going in detail. The temperature of disinfectant, increase in temperature result in more kill of water. More temperature means more killing of bacteria. The relationship between the time and temperature to effect in a given percentage of kill can be expressed as log 10 of the T1 divided by T2 is equal to E multiply with T2 minus T1 divided by 2.303 into R into T1 into T. This is the standard equation. So majorly in the three equations, questions will be asked, so that you have to remember that. Okay, this equation is very important. Here they ask a lot of questions. Log 10 of the T1 upon Tt is equal to E to the power E into T2 minus T1 divided by 2.303 into R into T1 T2. Okay, so suppose T1 and T2 time for the given, what is the T1 T2 time for the given percentage kill at a temperature T1 and T2 Kelvin. E activation energy in joule per mole, yeah, calorie per mole. R is the gas constant, that is 8.314 joule per mole into K, and K is 1.99, and T2 minus T1 is equal to 10. The useful ratio T1 T2, this is one equation. You can solve this equation. There is a number of numericals given over there. You can check it there, and you can solve one numerical how to use this. Okay, in indiabix.com also a lot of numericals are given on this chlorine doses, as well as the temperature of disinfectant and these constants. Okay, how to define the concentration of disinfectant, how to define the rate of killing of organisms. The second is the ozonation process. This is also most effective. So chlorination is done, and this is the ozonation. What time we have started? Based on this, we'll finish in 2 hours. Should be complete 2 hours recording. So I want to complete this ozonation part, and then we need more time actually. We cannot do it quickly. There are some numericals I have given here for the chlorine doses. Was this ozonation not too much portion, only 2 slides. After that I will be moving for the numericals, how we are solving a numericals for the chlorination related. So these are some numericals that the kinematics related to chlorine demand, and they have done it. Then water distribution networks and these things, how to go for the water distribution network and all that. Actually, I want to finish today for the water part, so I can easily move for the wastewater engineering. But since time is already gone, so anyway, no problem. We'll do not take too much of time for it. Design of distribution networks and Hardy cross methods, right? These are the things I want to discuss today. In next lecture we'll continue, but some numericals on chlorination we will do it. Just ozonation I will explain a little bit. Only I will take more 5 minutes, then we'll bind up the session. Okay, I'm a little bit faster because of the time constraint. You just go through in the slides, everything is there. You just go through. Please note down the important numerical formulas and try to do the numerical practice on that. And try to join some series, web series, what we call as these examination series for GATE के लिए जो web जो classes है ना, you can join those classes. Like AICTE is offering, Meet is offering, and IAS Academy is offering 400 they are charging, 500 they are charging for 40 papers. sample papers. There will be a time limit for 3 hours. It's like a prototype of your conventional gate paper, and then you will get practice through this 3 hours how to manage the questions. More and more problem you will solve, you will get the better result. That's all. Simple funda it is. Somebody is asking something. It will be online only. Online classes start. These classes only online mode. This is the online mode because these data we are going to send it to the AICT and the government portal. We are going to submit it, and these people are using these details. So that's why it is required. आकाश है, जमुना है, प्रणति है. Okay. Yeah. Just we are going to bind up this session. Just ozonation I will explain. Okay. I didn't give you the time in interval for in between. So as I told you, ozone is a very good oxidizer, very good disinfectant. Ozone is a form of oxygen with the molecular formula O3. It forms when oxygen in the air is exposed to the discharge of a powerful electrical current through air. It is a chemical water treatment based on the infusion of ozone into the water. Most powerful disinfectant. It can kill. Instant killing happen in the ozonation process. Ozonation is a type of advanced oxidation process involving the production of very reactive oxygen species able to attack a wide range of organic compounds and all microorganisms. Ozonation generally prefer for the wastewater treatment, actually sewage water treatment, not for this domestic municipal water treatment. Generally, ozonation is preferred for the industrial wastewater treatment also, because highly toxic water and the organic matter presents in these water, the impurities are the higher percentage. The BOD content will be very high, COD content will be very high. That's why ozonation is preferred. It's the most advanced method for the disinfectant. So ozone is produced with the use of energy by subjecting oxygen to a high electric voltage. So forming, we can say the making ozone is a very difficult task in the laboratory. So we need a big setup for the ozonation. Once the ozone is generated and storing and then using as a disinfectant is also a very costly affair. So ozone is produced with the use of energy by subjecting O2, oxygen, to high electric voltage or UV radiation. The required amount of ozone can be produced at the point of use, but the production requires a lot of energy and is therefore costly, removes color, taste, and odor, and volatile organic components present in a wastewater. And excess amount of iron and manganese also it can be removed. So the multiple functions, multiple impurities can be removed in a single ozonation process. Ozone exists in unstable forms always, so it needs to be generated just before the ozonation, as it cannot be stored. So ozone cannot be stored. Absolutely safe in any amount of ozone doses. Little residual power is required for it. So 1 kg of ozone required. If you want to produce a 1 kg of ozone in a laboratory, you require 0.80 kilowatt hour power for it. Air passes through the positive negative electrode and produces ozone. There's a complete setup you have to provide for it. Like this, you see this is the ozone treatment process, how the ozone is forming. We'll go from the simplest one here from there. So wastewater treatment plant effluent, we are getting it. After secondary treatment, then ozonation we are providing for the advanced disinfection purpose. And as I told you, there's a multiple function. It removes color, taste, and odor, and VOCs in excess amount of iron and manganese also. Except it removes all the microorganism, bacteria and microbial bacteria and pathogens. That is a separate function. But along with this, it helps in removing other impurities also. So this is the tank. This is the feeding pump. This is the O3 generator where the oxygen will be generated. This is the O3 analyzer where how much ozone we are generating, so we can analyze this percentage. And there is the O3 off gas analyzer. So all the meters, flow meters, analyzers are attached, and we can see how much ozone is generating and producing. We store direct applied. process. There's oxygen cylinder, oxygen concentration, oxygen tank they are provided, ozone generator they are this is a setup for ozone generation, and then how the treatment will be followed, that is another process. Okay, so like this process will happen here. These are certain advantages. Rapidly kills, the instant killing will happen for bacteria, viruses, and protozoas, right? Provide over a wide range of pH range, stronger germicidal properties than chlorination. No chemical are added for the water. Also efficient for organics degradation and inorganics removals. Any kind of doses will be fine for it. Removal, color, taste, odor, and magnesium iron present in the water. Relatively high equipment cost, as I told you. Require large amount of energy. Qualified professionals are required for it. Formation of potentially harmful disinfection by product. In case of brome, existent in water, no residual effect in presence of distribution system, potentially fire hazardous and toxicity associated with the ozone generation. These are some disadvantages for it. These are the reactions, how the ozone will be forming, chemical reactions. O2 is highly unstable, isotopes of oxygen, and then finally things will happen. Now this is one thing is remaining, relationship effectiveness of component of the free chlorine. This is the kinematics part of chlorine generation that will try to sum up with this formula, total amount of chlorine, that will talk later in next class. They are for the water distribution as well as for the Hardy-Cross method. So the next class, in within a 15 minutes, I will bind up the whole portion here, this whole portion, then we'll move for the sewage treatment plant. Okay. So that's all. We are binding up the session. It's okay for today. Yeah. Okay. Okay, then this PPT is available in the Google Classroom. I will just circulate there. Okay, you can download anytime. Thank you for the class. We will bind up the session. What is the time now? 6:17. Okay. Yeah. Pranati, Akash. Okay.